Hazır mısınız? Hazır değilsiniz. Okay, welcome to this last lecture in EE302. Well, the only topic remaining that we need to cover is something called observability today. So remember, when we have a state space representation of a system, I have x dot is equal to ax plus bu and y is equal to cx. The input of the system is given here and the output is given here. When we try to apply state feedback, we need to measure the state. So I need to extract this state from the system somehow. So this can be made by using a sensor on the system. Then I can actually try to feed this state back into the input side. Okay? And we learned that this is called state feedback. Okay? And it is quite powerful when we have controllability of the state space representation. If the state space representation is controllable, then we can place the closed loop poles of this architecture anywhere we like in the complex plane by choosing a suitable K. But I told you that this has some disadvantages, and the disadvantage is that I need to measure the state somehow. And measuring the state would mean that I need to put additional sensors into the system, which might be sometimes impossible, and which might be sometimes just costly. Okay? That actually means that measuring the state might not be the optimal solution that we might try to use here. So instead of trying to measure the state, sometimes we can come up with some algorithms which can calculate an estimate of the state by using only the input and the output measurements from the system. So this is a computer algorithm somehow, or it's a differential equation solver actually in a computer. So you take the data U and you take the data Y. And from this, giving these to a computer, to a differential equation solver, we can come up with a differential equation somehow. And that differential equation might give us an estimate of the state. This estimate of the state is called x hat. Okay? And we want this x hat to actually converge to the actual state of the system quite in a fast way. Okay? Now, instead of feeding the actual state of the system back, we can try to feed the estimated state back onto the input side. Okay? So we can try to apply state feedback by using this computer algorithm. So such an algorithm is called an observer in control theory. Observer. And sometimes it is called state estimator. And there is another name. And there is another name which is called in signal processing, it is called filter. Okay? In this course, we saw only deterministic systems, meaning that our systems do not contain any noise terms. Okay? But in general, in control systems, we start to have defined noises in our systems, so these X's would become actually stochastic processes. Okay? So I have BU plus GW. This W becomes a process noise in the system. And similarly, the measurement equation turns into the following: CX plus HV. And V is the measurement noise in our system. So in general, we have stochastic systems in control, and we can actually try to design observers for those stochastic systems. And when we try to do that, generally, the observers are called filters in that case. If you heard the name Kalman filter, then it is the optimal state estimator, in some way optimal observer for a stochastic linear Gaussian system. Okay? So this observer concept is related to things called filters or Kalman filters, which are just observers for stochastic systems. So this type of things would appear really a lot in practice. So here, I have told you that in state feedback, the state feedback is always successful when the closed loop system is actually when the open loop system is actually controllable. Okay? So a controllability property is a nice property that we can have for state feedback. Similar to controllability, we have another property for which actually shows us the ability of us to design successfully an observer for a system. So there is another property that is called observability, which enables us to design an observer for a state space representation in a successful way. In a successful way, I mean that this x hat will be converging to the actual state x with any speed that we like, as fast as we like. And that property is, as I told you, observability, and that is the last topic of this course. If you look at these notes, we are at page 67 towards the end, and the topics related to the final exam will stop at page 71. We won't see observer design. We won't see how to come up with this algorithm, how to come up with a differential equation, which is going to give us some x hat, which is going to converge to x. Okay? Observer design will not be included, but observability is the last topic that we need to cover here. So let us define what observability is. Definition. System x dot is equal to ax plus bu, y is equal to cx, is said to be observable if and only if it is possible to calculate the initial condition x0 exactly from the knowledge of the output y and the input u over a finite time interval So this is the definition of observability, and it tells us that it is ability of us to do something. What we need to do for a system to be observable is that by observing only the input and the output of the system, I need to be able to calculate the initial condition of the state space representation exactly. Okay? We need to be able to calculate the initial condition. So now let us try to understand it. Why do we need? So in this case, for state feedback, we need x of t, okay? State at time t. We need that for state feedback. But observability is related to the initial condition of the system. Why do we need initial condition for calculating x of t? It would be better, actually, if we know x of t directly, okay? But actually, knowing only the initial condition of this system, this computer algorithm can always calculate what the state at time t is. This is because we have a deterministic system in this case, okay? So we have x dot is equal to ax plus bu. We have this type of equation, and we know that the solution of such an equation is only dependent on x0, the initial state, and the input u. If I know the initial condition, if I know the input of the system, because I know this differential equation, I can solve x of t for all time. Okay? An observer would always know the input of the system. Okay? It knows the input of the system. Okay? So the only thing that I need for calculating x of t at any time is the initial condition. Observer knows this. Observer will know a and b. So the only thing that the observer needs in order to be able to solve for x of t for any time is going to be the initial condition itself. If it knows the initial condition itself, we can use a differential equation solver in a computer, and we can solve this differential equation for that specific initial condition and for the input that we are measuring. Okay? So that is why observability is defined as the ability of us to be able to calculate the initial condition of the system exactly from the knowledge of the input and the output of the system. Okay? So that is the meaning of this definition. Again, our system is going to be looking like this. X dot is equal to AX plus BU and Y is equal to CX. In general, from these triple A, B, C, observability is only going to be dependent on two of these. Okay? So for controllability, the dependence was on A and B. Okay? For observability, the dependence is going to be on A and C. So B is really irrelevant for observability. Okay? So we can write a remark here. Observability, because observability is related to the output and the state itself, it's irrelevant to the known input. Observability is only related to A and C and not to B. Okay? So that actually means that while trying to understand about the observability of a system, we only have to look at these A and C matrices, and we can determine whether the system is observable or not. We don't really have to know what B is for talking about observability. Let us look at the following example. I will again give you some systems which are not observable, or sometimes they will be observable, and we will try to understand the reasoning of us to be able to see those. So let us say that we have this equation. I have x dot is equal to this, and y is equal to, let me say, 1, 0, x. Okay? Here I haven't written any term related to B. Okay? So this system just gives a response related to its initial condition. Input is irrelevant. Okay? So I'm just going to be looking at this A and C, and we'll try to understand if this system is observable or not. So what does that mean? By measuring only the output, input of the system doesn't exist currently. By measuring only the output, can I find the initial state from exactly from the output? By measuring only the output of the system, can I find the initial state of the system exactly without any error? Okay, that is the task in observability. So I will write the individual equations of the system here. X1 dot is equal to minus x1. X2 dot is equal to minus 2x2. These are the differential equations of the system here. And I can write the output equation. Y is equal to, in terms of x1 and x2, what is y? In terms of x1 and x2, what is y? Y is just x1 in this case. Okay? So here I can easily solve these differential equations. These are x1 of t is equal to e to the minus t x1 0. That is my initial condition. x2 of t is equal to e to the minus 2t x2 0. Okay? I have my initial condition given there. Okay? So here, for observability, by observing only the output, observing only y, because input doesn't exist in the system, observing only y over a finite interval, the question is, can I obtain perfect information, perfect knowledge of x1 0 and x2 0? These are the initial conditions. So now if I would like to draw what y of t is. This is y of t, this is t here. Y is x1 of t, this is e to the minus t, x1 0. Okay? So if this is x1 0, this is going to be what my output would be looking like. Okay? Now the question is, by just looking at this figure, this y of t, over a finite time interval, can I calculate x1 0 and x2 0 perfectly, exactly, by just looking at this figure, the output waveform? can I calculate x10 and x20 perfectly? I will not be able to do it. This is only related to, this output is only related to x1, okay? That is why I will not be able to calculate anything related to x20 for this system. The initial condition for the second state will be forever unknown to me with this output. That is why such a system is not observable, okay? Because by looking at the output only, I will not be able to calculate the whole initial condition set of the system. So now let us try to look at the following example. Now I will give you an observable system example. The equations will remain the same. Okay? And y is equal to, in this case, 1, 1, x. Okay? Again, I have the same state solutions. These solutions are still correct for this system. That is the same system. But in this case, output y of t is equal to, I have x1 plus x2 as the output. Okay? And when I sum these two state variables, I will get the following: e to the minus t x1 0 plus e to the minus 2t x2 0. Okay? So we see that the output is again going to be a decaying exponential somehow, because both of these terms are decaying. There might be some initial transients, but still it's going to decay to 0. So the output, I will here try to draw it once more again as a decaying exponential. The initial value is what? What is the initial value of the output? This is going to be x10 plus x20, okay? That is the initial value of the output. And we are observing this output for all time, and I will look at only a finite time interval. Suppose that I evaluate this output at the time instant t is equal to 1. T is equal to 1 second is an arbitrary time instant that I take here. Okay? I could have taken t is equal to 0.1 seconds. The result won't matter. Suppose that I take t is equal to 1 and I look at the value of the output. This is the value of the output at time t is equal to 0. The value of the output at time 1, y1, is going to be obtained when I substitute t is equal to 1. Okay? So this is going to be e to the minus 1, x10, plus e to the minus 2, x20. Okay? So now I can check what can I obtain? What I can obtain by using these two values of the output. If I look at y0 and y1 here, okay, this is equal to, I can actually write these equations in the form of a matrix vector multiplication. And I can actually come up with the following. Suppose that my unknown initial conditions are here. Okay? These are two values given like this. And I have a matrix here, a 2 by 2 matrix. So we see that this is 1, 1. So y0 is the summation of x10 and x20. And y1 is again a linear combination of x10 and x20, now with the coefficients e to the minus 1 and e to the minus 2. Okay? So I have here e to the minus 1 and e to the minus 2. Okay? So now the question is, by observing this output over a finite time interval, for example from 0 to 2 seconds, okay? By observing the output over this finite interval, can I find the initial condition of the system exactly? I know this y0 and y1, I measure this, okay? And I don't know this, but I know that there is a matrix multiplication here, and I will know what this matrix is. Do you think I can invert this matrix to calculate x10 and x20 exactly from this equation? Yes, this matrix is indeed invertible. How can I check if it is invertible or not? Calculate the determinant. We easily see that the determinant is e to the minus 2 minus e to the minus 1, which is non-zero. Okay, that actually means that such a matrix is invertible, and that means that I can calculate x10 and x20 exactly from this equation, but from y0 and y1 values. That actually means that I can indeed calculate x10 and x20 for this system by observing the output over a finite time interval exactly. That is why this system is actually observable. Okay? So by seeing only these two examples, you might think that observability is related to the zero elements in the C vector. Okay? But actually, we are going to see that it is not. Okay? So here, we have seen that because of this zero element, this system became non-observable. And because of this additional one here, this system became observable. Okay? But in general, a system sometimes can be unobservable even if all of the elements of C are actually non-zero. Okay? Sometimes that can actually happen. And now in the last example, we are going to see that type of system. So now suppose that I have this last example here. And in this case, I have x dot is equal to -1, -1, 0. I change this system, and it is in this case given like this. And let us say that y is equal to 1, 1, x. Okay? Again here, the C vector is completely composed of non-zero elements. Okay? And now I will try to check if I can do the same thing here that I did for this system. Okay? In this case, I know that x1 of t is equal to e to the minus t x1 0, and x2 of t is equal to e to the minus t x2 0, and y of t is the summation of the states, and they are going to be e to the minus t x1 0 plus e to the minus t x2 0. Okay? Now I'm assuming that I measure the output over a finite time interval. Okay? If I do that measurement and if I calculate such a matrix equation, then the question is, will I be able to solve that equation? Okay? In this case, if I do that, y0 is x1 0 plus x2 0 again, and y1, for example, e to the minus 1 x1 0 plus e to the minus 1 x2 0. Okay? In this case, if I write the matrix equation here, then I will see the following. Then the matrix here will be 1, 1, e to the minus 1, e to the minus 1, x1 0, x2 0, and I will have here y0 and y1. Do you think in this case I will be able to find the actual initial conditions exactly from such an equation? What is the reason? The determinant is 0 and the matrix is not invertible. You can actually see this thing here as well. E to the minus, this is e to the minus, this output here is e to the minus t times x1 0 plus x2 0. Okay? That is what the output of the system is. Okay? So I have y of t in this case is e to the minus t times x1 0 plus x2 0. Okay? So now suppose that I consider a single initial condition vector. Let me say that this is 1 and minus 2. Okay? Tell me another initial condition vector for which I will observe exactly the same output. Give me another initial condition vector. This is initial condition 1, and I have initial condition 2. Tell me another one for which I will observe exactly the same output.
0 minus 2 and 1.
Birisi söylesin.
Minus 2 and 1.
Minus 2 and 1. Okay? In this case, I will get exactly the same output from the system. That actually means that by looking at only the output of the system, I will not be able to obtain the information of the initial conditions exactly. That actually means that I will not be able to obtain the state information for this system by looking at the output only. So this system is again not observable, unfortunately. Okay. So in general, actually, we don't reason about observability by writing the equations of the system in this manner and then trying to understand if it is observable or not. In general, just like the controllability, we have a test for that. Okay? Remember, for controllability, we were forming a Q matrix, which was formed B, AB, going until A to the n minus 1B, and then we were looking at the determinant of such a matrix. And for observability, we have a similar condition that we can use to check for observability. Okay? And now we are going to write this as a theorem. A system x dot is equal to ax plus bu and y is equal to cx is observable if and only if determinant of some matrix W is not equal to 0, where W is formed as follows. You form the first row with C, and the second row is going to be CA. The third row is CA squared, and these are going to continue until CA to the power n minus 1. Okay? This matrix where W is called the observability matrix. Okay. So again, observability can be checked quite easily by looking at the determinant of a matrix. And we can actually do that thing, we can try to apply this theory to actually this system. Okay? For this system, I have C is equal to 1, 1, and A is equal to minus 1, minus 2, 0, 0. Okay? Now, if I calculate the W matrix, how many rows will I write? 2 rows only. Here, the n is 2 for this example. Okay? N is the dimension of the state vector. Okay? N is 2, and since n is 2, the highest power that I'm going to write of A here will be 1. That actually means that the W matrix in this case is C and C times A. So C is 1, 1, and C times A. If I multiply a square matrix by a row vector from the left, I am weighting and summing its rows. Okay? I will multiply the first row by 1, and I will multiply the second row by 1, and I will sum them. Okay? This is going to give me minus 1, minus 2 here. CA is minus 1, minus 2. And that actually means that, and the determinant here, determinant of W here, is going to be minus 1, which is non-zero. That is going to mean that this system is actually an observable system. If I do the same thing for this system instead, in this case, C is this, and A is this one. So I can write W for this example as 1, 1. This is C. And C times A is going to be the summation of the rows of A. Minus 1, minus 1 here. So we see that in this case, determinant of W is indeed 0, making the system unobservable. So here, we have a remark at this point. Remember, we have seen some state space representations that was called controllable canonical form. And when we saw the property of controllability, we saw that a state space representation in controllable canonical form was always controllable. Okay? And another representation that we saw was called observable canonical form. And now we're going to see that a system in observable canonical form is always observable. Let us write a remark. A system x dot is equal to ax plus bu, y is equal to cx, where a and c are in observable canonical form, is always observable. And I will show this using a very simple example. So I will here consider g of s is equal to s plus 1 and s cubed plus 5s squared plus s plus 10. I have to first remind you actually what the observable canonical form would actually look like. So here, if I have g of s in the following form, g of s is equal to, let us say the transfer function b1s to the n minus 1, b2s to the n minus 2, going until bn, okay, and I have s to the n plus a1s to the n minus 1, going until an, okay? This is the transfer function that we have found observable canonical form for, and these are the A, B, C vectors. Y is Cx. When we look at an observable canonical form state space representation, C is always filled with zeros except for its last element, which is 1. And B is filled from the numerator coefficients in reverse order, Bn like this. And A is, its last column is minus A1, minus A2, going until minus AN. Remember, this is the transpose of controllable canonical form A matrix, okay? And the main diagonal is 0 except for the last element, and sub-diagonal is composed of 1s, and I will have zeros everywhere else. This is a state space representation in observable canonical form, and I can find the corresponding state space representation for this G of S. Okay? So in this case, I have a 3 by 3 A matrix, X plus BU, and Y is equal to CX. For that transfer function, I have a 3 by 3 A matrix, and this is 3 by 1 and 1 by 3 here. The C vector is given like this, and B vector is going to be, what is going to be this element in the B vector? I have done this several times here. This thing here, remember, if you compare this general form with this one, I see that the numerator should start from a power which is 1 less than the power here. The power here is s cubed, so that means that the powers here should start from s squared. So this thing is 0s squared plus s plus 1. That actually means that I need to write here 0, 1, 1, given like this. And finally, I have minus 5, minus 1, and minus 10. The diagonal is 0 except for the last element, and sub-diagonal now is 0. In controllable canonical form, I have the super diagonal, which is composed of ones. And now all I have to do is to calculate this observability matrix, which is called W. Okay? This W is, in this case, n is equal to 3. That actually means that W is going to contain 3 rows, C, CA, and CA squared. Okay? So here C is, in this case, 0, 0, 1. Okay? And if I multiply C with A from the right, C times A, I will take this vector here, put it here, and I will multiply this matrix with C. What is it going to give to me?
Last row.
Last row it's going to give me. Okay? So I have 0, 1, and minus 5. And then I need to calculate CA squared. Here you can calculate what A squared is first and take its last row. Okay? But it is not really necessary. In this case, CA squared is nothing but CA times A. Okay? That actually means that if I take this row vector, okay, and if I multiply it once more by A from the right, then I'm going to obtain the resulting row vector. So I will take 0, 1, minus 5, and I will multiply this matrix like this. I will multiply the first row by 0. The second row is going to be multiplied by 1. So I will have 1, 0, minus 1. And the third row is going to be multiplied by minus 5. So 0, minus 5, and plus 20, 25 here. Okay? And that is going to give me, when I sum these, I will get 1 and minus 5, and I will get 24. Okay? And if you do the same thing for the general observable canonical form with order n, then you would always obtain a matrix in the following form. So you will have all ones here on the cross diagonal, and you will get zeros everywhere here, and you will get some elements which are not important in this part. Okay? If you calculate the determinant of such a matrix, you would always get a non-zero number. And if I calculate the determinant here, I have plus, minus, plus here. The determinant of W here is plus 1 times the 0, 1, and minus 5 determinant. Okay? And that gives me minus 1. Okay? And here we see that this determinant is non-zero, but for the general observable canonical form, it's going to be non-zero for any size of matrices. Okay? Yes.
The way that we can say that this cannot be non-zero is because of the triangular matrix.
No, this matrix is not triangular. Triangular would either be upper triangular or lower triangular. Triangularity is related to the main diagonal, not the cross diagonal. Okay? So here it's not really difficult to see this. If I would like to calculate the determinant of such a matrix, I will start from the first row. Okay? This is 1 times determinant of the remaining matrix. Okay? And here I will take the smaller determinant as I will have minus 1 or 1 times the smaller matrix. If I continue in this manner, you will see that you will never encounter a zero anywhere, and you will be able to take the determinant. You see that it's a non-zero number. It's either plus 1 or minus 1 at the end. It's never another number. Okay? So now I will just look at the following system. X dot is equal to, let me say, minus 1, minus 2, 0, x plus 0, 1, u here. And I will write the output equation here. Y is equal to 1, 1, x. Okay? So here I will check if the system is controllable or not. Okay? Q matrix in this case is B times AB, B and AB. And here B is 0, 1 and AB is 0, 0, minus 2. Okay? AB is 0, minus 2. Is the determinant in this case 0 or non-zero? It is 0 in this case. Determinant of Q is equal to 0. Okay? And now I will check observability. W is C and CA. Okay? Here C is 1, 1 and A is minus 1, minus 2 here. Determinant of W is non-zero. Okay? In this case, the system is not controllable, but observable. Okay? So I have something like this, some properties given like this. Now I will calculate the transfer function of such a system. The transfer function is obtained by the following formula. G of S is equal to C Si minus A inverse times B. Okay? So here Si minus A is the following. Si minus A is equal to S plus 1, S plus 2, 0, 0. And when I try to calculate the inverse of this matrix, I will calculate the determinant. Determinant of this thing is S plus 1 and S plus 2 multiplication. And numerator is going to be the adjugate matrix. Change the places, change the signs. S plus 1, 0, 0. Okay? Now I will multiply this inverse. This is Si minus A inverse. I will multiply this with C from the left. C is 1, 1. Okay? And B from the right. It is 0, 1. So we see that this multiplication is going to get the second column, okay? And this multiplication is going to sum the two rows, okay? What is the result of this multiplication? The numerator, I am asking the numerator. It is going to be just s plus 1, okay? S plus 1, s plus 2, okay? So we see here that these s plus 1s are actually cancelling, okay? And the transfer function turns out to be 1 over s plus 2. So when the system is not controllable, or when it is not observable, such things can happen. They will actually always happen, and it's because of this. If I look at the equations of this system, it is x1 dot is equal to minus x1, and there is no input here. x2 dot is equal to minus 2x2 plus here. When I look at these equations, we see that x1 equation is independent from the input, okay? And x2 is dependent on the input. We see that here, this part of the system, x1 variable, is not controlled by the input at all. It behaves by itself, without any input at all. That actually means that some part of the system is actually not connected to the input. Some part of the system is not connected to the input, and that is the part related to the eigenvalue minus 1 here, okay? The part related to the eigenvalue minus 1 is not connected to input, and we see that it is cancelled in the transfer function of the system. A transfer function is a relationship between the input and the output of the system. If some part of the system is not connected to the input, then that part actually cancels from the transfer function. The same thing can happen when the system is not observable. If the system is not observable, some part of the system is not connected to the output actually. And since transfer function is a relationship between the input and the output of the system, those parts of the system will again cancel when the system is unobservable. Okay? I'll just show you this final example system. I will take the same system, right? X dot is equal to minus 1, 0, 0, minus 2, plus 0, 1, u, and I have y is equal to, I will have 1, 0, 0, x. Okay. In this case, the system equations are still the same. Again, I see that the system is not controllable. A and B are the same. The system is not controllable. But in this case, I will see that the W matrix is going to be C and CA. Okay? It is 1, 0, and CA is going to be the first row of this matrix, minus 1, 0. We see that determinant of W in this case is 0. That actually means that the system is not observable. Okay? Not observable. So the system is not observable and not controllable at the same time. Okay? So here again I see that which part of the system is not controllable. The part of the system related to the eigenvalue minus 1 is not controllable. The second part is controllable. Okay? What about observability? Which part of the system is observed? Which part of the system is connected to the output? The first part. The part related to minus 1 is connected to the output. The part related to minus 2 is not connected to the output. That is the unobservable part of the system. So I see that minus 1 is not controllable, but it is observable. But minus 2 is controllable, but not observable. Okay? So all parts of the system have some problem related to input and the output. One part is not connected to the input. Second part is not connected to the output. Okay? In this case, what is going to happen to the transfer function?
0.
Yes, it's going to be 0. Let us try to calculate that. So I have s plus 1, s plus 2, 0, 0 here. I will calculate the inverse of this matrix. It is going to be again the same. s plus 2, s plus 1, 0, 0 here. I will just write here 0, 1, and I will write 1, 0 here. Divided by s plus 1, s plus 2. Okay? Now I can actually calculate, this is going to take the first row, and this is going to take the second column. Okay? But first row, second column element is 0 here. That actually means that the transfer function is 0. What is happening here? All parts of the system are either not connected to the input or they are not connected to the output. That means that they are going to disappear from the transfer function of the system, which is an input-output relationship. Okay? So here, when we have a linear time invariant system, we can always divide it into some parts. It can be controllable parts, and there can be observable parts. These parts are both controllable and observable. There can be controllable parts and non-observable parts. There can be uncontrollable parts but observable parts, and there can be uncontrollable and unobservable parts. Okay? Uncontrollable parts of the system are not connected to the input. Okay? Only controllable parts of the system are connected to the input. And only observable parts of the system are connected to the output. Okay? So we have something like this. So this is our system here, and we can divide our system into these parts. And we know that the transfer function is the relationship between the input and the output of the system. Which parts of the system will determine the transfer function of the system? Which parts in these 4 parts will determine the transfer function of the system? Only the parts controllable and observable will actually determine the transfer function of the system. Only those parts will not cancel. Okay? The rest of the eigenvalues of this matrix will always cancel when we have uncontrollable or unobservable parts. And this part will not affect the output at all, and this part is going to be connected to the input and the output. So this is linear system theory, and it gets really magical after some point. But this is the end of 302. Yes. Yes, in general, when I look at these simple systems, because the matrices are diagonal, I could do this quite easily. But in the general case, you can still make a decomposition. It's going to be possible actually. Even if the matrix is filled with non-zero elements, you will be able to do this type of decomposition, and it has a specific name in linear system theory. If you stay here in the graduate courses, if you take the course EE502, for example, in this example, it's completely related to this type of issues related to linear system theory. Okay? That's all for 302. Thanks. Efendim?
Yarım saat daha